Hey everybody, Mr. Judson here. Hey, I still have one Pi Day project that nobody's claimed, so if this happens to be yours, let me know. Everything else I've got points on and I've got it in the grade book. So, alright, so we talked about this last week. Chapter 8 is really about, what happens when we have integrals that we don't know how to solve. It doesn't fit one of our basic formulas. And so we're going to start with one of the strategies today, and it's called integration by parts. What it means is we're going to break this integral down into different parts that we can kind of do something with and then go ahead and solve. And so first we have to build our rules for this. Now, one of the nice things about Chapter 8, I think I told you guys Central Washington really likes Chapter 8. One of the nice things is anything that comes out of Chapter 8, they will say, solve this integral using integration by parts. And so they'll tell you what method to use. You don't have to remember or, okay, I don't know what to do, so let's just try one and see what happens. That can be really time consuming. So that's a good thing. They'll tell us when to use this method. So what we do is we start off with the derivative of two things that are being multiplied, so we're just using the product rule. Normally I would say derivative of the first times the second plus leave the first alone and then times the derivative of the second. I think our book switches that around. So I just wrote it down the way that the book does. And so what we need to do is we need to use this to build a strategy. And so what I'm going to do is I'm going to rewrite this. This part will just stay the same. d dx of u times v. And I'm going to change this to u times, this would be the derivative of v with respect to x. So dv over dx. Plus v times, this would be the derivative of u with respect to x. So du over dx. So just like we say y prime is the same as dy over dx, u prime is the same as du over dx. And same thing over here, v prime is the same as dv over dx. And so then what I want to do is I want to integrate everything here with respect to x. So I'm going to integrate this with respect to x. I'll integrate this with respect to x. And I'll integrate this with respect to x. So on this side, if you take the derivative of something with respect to x, and then you turn around and integrate it with respect to x, it should come right back to the same thing. So this is just equal to u times v. On this side, I'm going to cancel the dx's. Same thing here. And so what I get is the integral of u dv plus the integral of v du. And then what I'll do is I'm going to move this piece over to the other side and subtract it. So I've got u v minus the integral of v du, and that's equal to the integral of u dv. And so now let me just flip this whole thing over. The integral of u dv is equal to u times v minus the integral of v du. And this right here is really our rule for integration by parts. We're going to do the integral of two things that are being multiplied. We'll kind of talk about this in a second. And whatever those two things are, it has to equal this over here. And so I guess the first thing we have to ask is, well, what do you mean two things here? Well, this says the integral of u dv. It's not this says in terms of v, but over here I've got the variable u. And so these are my two parts. When we say integration by parts, these are the two parts right here. And so what we want to do is we want to say that u is going to be something that is easy to differentiate and it becomes simpler. Okay, so u is something easy to differentiate, and it becomes simpler. So when I say it becomes simpler, I mean something like x squared, when you take the derivative, it becomes 2x. My exponent decreased, and so that's considered a simpler expression. If I take the derivative of something like a secant, and that becomes a secant times a tangent times the derivative of the angle, I'm not sure if that's simpler. Okay, we want this to be easy to take the derivative of, and it becomes simpler. And then dv is something easy to integrate. Because see, if dv is something that's easy to integrate, whatever I let dv equal, once I integrate it becomes just v, and I'm putting that expression here and here. U is something that's easy to take the derivative of, so I'll put u here and the derivative of it here. Okay, that's the plan of integration by parts. Let's work through an example. That'll help this make a little more sense. All right, so here's an integral that if I had to integrate this, the first thing I would think is e to the u prime dx just equals e to the u. But the derivative of the exponent is not x, and so I would get stuck on this. And so this would be a good candidate for integration by parts. So here's our rule. Remember, u is something that's easy to differentiate, dv is something that's easy to integrate. So the first thing I want to do is I want to assign those two things. So what am I going to let u equal, and what am I going to let dv equal? Okay? So u is something that's easy to take the derivative of, and it gets simpler. So that'll be x. So that means that when I take the derivative, and I'm going to do this implicitly, okay, because I see a du up here, so I want to see a du down here. So the derivative of this is 1, and I just took the derivative of u, and the derivative of this is 1, and I just took the derivative of x. dv is going to equal the part that's easy to integrate. And so usually that's the rest of this stuff that's written here. The dx will always go with this dv part, and then whatever was left here. So e to the x dx. And so now what I need to do is I need to integrate both sides. So the integral of this would just be v. The integral of e to the x dx is just e to the x. And we're not going to worry about the plus c yet, because we're still going to have another integral that will give us that plus c at the end. Okay? All right. So the integral of u dv, here's u, here's dv, now equal to u times v, so that's x times e to the x, minus the integral of v du. V is equal to e to the x, du is equal to just dx. And now when you look at that, you'd think, well, that's an integral that I can do. That's not too bad. So this is going to be x times e to the x minus integral of e to the x is just e to the x plus c. And that plus c here is all the constants that we would have had throughout the problem. We'll just combine them all into one and call it that right there. And there's my answer. So I guess the question now is, how do you check to see if this really is the answer? Well, I just did an integral, so if I take the derivative of this, I should get that at the end. So let's just try it and see. If I took the derivative of this, I'm multiplying two things, so I have to use the product rule. So I'll take the derivative first, which is 1, times e to the x, plus, leave that x the way it is, times the derivative of this, which would be e to the x, minus derivative of this, which would be e to the x. Derivative constant is 0. These two add up to 0, and that's what we started with. So yeah, that checked out. All right, so you guys go ahead and try this one. Remember, you always want to start out by trying to figure out what am I going to let u equal and what am I going to let dv equal. Something easy to take the derivative of and it gets simpler. Something easy to integrate. And it's nice if it gets simpler, but I'm not sure it always does. We're not worried about that. Here we want it to get simpler. You guys go ahead and try this one. All right, so when I look at this one, here's my two parts. I have to figure out which one's going to go where. We don't know how to integrate a natural log. So it can't go here. Right? That can't happen. The only thing that can go here is the x. The natural log has to go here. So, it really doesn't matter if it gets simpler. It's the only option we have. X dx. Okay. Remember that dx has got to be one of the parts here, and you always want to assign it to the dv because once we integrate, we need a dv and a dx in there. All right. So as soon as I take the derivative of this, I would say that it does get simpler. Derivative of a natural log is u prime over u, so that would be 1 over x. That is, fraction, but it is simpler than a natural log. Here when I integrate both sides, so I'll integrate this side, I'll integrate this side, I get v equals x squared over 2. And so now we just need to set it up. I've got u times v, so that's a natural log of x times x squared over 2 minus the integral of v du. So x squared, oh, I forgot up here, when you take the derivative, I did u prime over u, derivative of x was 1, and I just took the derivative of x. I got to get that in there, otherwise when I integrate, I don't know what it's with respect to. So x squared over 2 times 1 over x dx. And so I can cancel an x with an x here. I'll move that 1/2 to the outside, so I get minus 1/2 the integral of x dx. For this, I'm just going to put the x squared over 2 out in front, so I don't think it's part of what I'm taking the natural log of. So I've got x squared over 2 times the natural log of x minus all this, which means I'm going to have x squared over 2 natural log of x minus 1/2 times the integral of x would be x squared over 2 plus c. So my final answer here, x squared over 2 times the natural log of x minus, I'm going to call this x squared over 4 plus c. And if you want to check this on your calculator, that's fine. Take the derivative of this on the calculator, see if you end up with that right there. Even though we know that this whole semester is about integrals, and our Central Washington test will be about integrals, I still think it's good to keep it in our head, derivatives, because a lot of times people get those rules switched around, and they're doing an integral, but they actually do a derivative instead. So if we keep on practicing doing this on our own by hand, that's probably not a bad thing. All right, so this time we got the integral of x sine of x dx. Normally I would think substitution, let u equal the angle, and then take the derivative of it and hope that's it. But again, here it's not. So we want to use this idea of integration by parts. Remember, Central Washington will tell you when to use integration by parts. So I don't know that I would ever just go and use that on my own for that test that's coming up. I would wait until they tell me to use it. Okay, so let's figure out, what's u going to equal and what's dv going to equal. All right, so something I can take the derivative of and it gets simpler. That sounds like just x. I do know how to take the integral of sine of x. So that's fine if we put that there. So let's see, derivative of that means du is just going to equal dx. Here if I integrate both sides, then the integral of this will be v. Integral of a sine of x is a negative cosine of x. And so now this integral is going to equal u times v. So that's a negative x cosine of x. I'm multiplying these two pieces here. Minus the integral of v du. Well, I'm subtracting a negative, so that goes to plus. And then I've got cosine of x dx. And so the integral of a cosine is just a sine, so I get negative x cosine of x plus sine of x plus c. There it is. So let's just check it by hand. If I take the derivative, I've got two pieces here, so I've got to take the derivative of the first, which is a negative 1, times the second piece, plus, leave the first the way it is, times the derivative of the second, which would be, derivative of cosine is a negative sine of x, so negative times a negative would be positive. And then the derivative of this would be a cosine of x. Derivative of a constant would be 0. Those add up to 0. That's what I started with. So we got that right. All right, let's try one more. All right, so again, I want u to be something that gets simpler, and dv is something that I know how to integrate. This is one of our basic formulas. So I'm going to call that secant squared of x dx. I do know how to integrate that. Again, u is just x. That means that du is going to equal dx. And when I integrate both of these, integral of dv is just v. Integral of a secant squared, that's a tangent. Right? If you take the derivative of a tangent of x, you get a secant squared of x. And so now, hey, just something to remember. We always get to use a note card on our Central Washington test. This would be a good thing to write down. Here's our integration by parts. I want that to be something I can take the derivative of, that to be something I can integrate. That kind of reminds us of a lot right there. All right, so this integral will equal the integral, or will equal u times v, so that's x tangent of x, minus the integral of v du. So a tangent of x dx. This just stays the same, x tangent of x minus integral of a tangent. Think of this as sine over cosine. That's a u prime over u, right? Sine over cosine, that's u prime over u. And so what I get is, let's see, the derivative of a cosine is a negative sine. So this is actually a negative natural log absolute value of cosine. So I'm going to subtract a negative, which means that becomes positive. Natural log absolute value of cosine of x plus c. All right, there it is. Integration by parts. We'll do some more of this tomorrow because some of them do get a little more complicated. We'll just kind of work with the easier ones for today, but we'll get a second look at it tomorrow. All right, we're going 3 days this week, you guys. We'll have videos on Tuesday, Wednesday, Thursday. That's something we have to do. I mean, if we want to get through our material and have enough time to do a decent review for that Central Washington final, we've got to do that. Got to do it. All right, here's our assignment. All right, so I think I got off at some point. I did assignment number 9 twice. So on Thursday, that I think I called that number 10. That should have been number 11. Today we're on number 12. Page 531, we're going to do 8 and then 10 through 20. We'll do all those. So I'll have some even answers up for you guys on tomorrow. I'll work those out, and you can check those answers that way, or you can just check with your calculator. But make sure we're checking. That's really, really important to us. All right, that's it. That's all we have for today. See you guys tomorrow. Stay safe.